I want to talk about a differentiation rule now called the chain rule. And it's actually a rule that's being used every single time you take a derivative. It's just that the derivatives you have taken so far have been ones that were intentionally created such that the chain rule, when used, didn't noticeably in any way affect the outcome. But regardless, the chain rule was in use at all times. And here's where the chain rule becomes necessary. Let's say we had a function f of x equaling the square root of x squared plus 1. The rules we have up to this point would not allow us to take that derivative, mainly because f of x is a composition of functions. F of x is created using a lowercase function f and a function g. All right, and in the case of this f of x, the lowercase f is the square root function, and the lowercase g is the x squared plus 1. All right, so in other words, what I'm saying is to create this f of x, you have to take this g and place it inside of that f, and that is how that function f is created. And since we are in a situation here where we have a function inside of a function, none of our differentiation rules tell us how to do that. Again, f prime here would be the same as taking f of g of x and taking that derivative. Now, we've learned how to take the derivative of f plus g and f minus g and f times g and f over g divided by g, but f of g, no, we have not. So for that purpose, we need the chain rule. The chain rule, and I'm going to state it here without proof. The proof's in the book if you really want to see how it's proven. But the chain rule states that f prime of x, when f is this composition that I'm talking about, is equal to f prime of g of x times g prime of x. Now that's writing it in Newton's notation. If you put it in Leibniz notation, which you see very frequently, it says that dy dx is equal to dy du times du dx. Now, which notation is better? Well, it really doesn't make much difference. But for the sake of example here, I think I'm going to stick with this one. What this is basically saying is if you want to take the derivative of a composition, you take the derivative of the function that's on the outside first, while making a carbon copy of the function that was on the inside and leaving it inside, and then you just multiply by the derivative of that innermost function. So back to our first function, our f of x was the square root of x squared plus 1, which I would choose to write as x squared plus 1 to the 1/2 power. So therefore, f prime of x, here's what I'm going to do first. If you recall, we said the outermost function was the square root function. So I'll take the derivative of the square root function first. Power rule says the 1/2 comes down. The 1/2 gets reduced by 1 and becomes a negative 1/2. And the chain rule says that the function that was inside gets copied over. Right, so this is the f prime of g portion. The chain rule then goes on to say you must multiply by g prime. And g is the x squared plus 1 that was on the inside. So g prime will be a 2x. Now, something I like to say to my calculus students on a fairly regular basis is that you must at all times keep in mind what's a constant, what's a variable, what's a function, etc. All right, now something that most or hardly any other instructor I've ever seen will do is to go on to say that, most books would say that this large f is one function inside of another. There's, though, always, in my opinion, one more function on the inside. So I would go back and do something the book wouldn't do, is I would add to this list an h of x, a third function, that being the identity function. And it may not make a lot of sense right now, but I would go on to say that I'm going to say times the derivative of that last innermost function, again being an identity function, and I'm going to add a times 1 to that. Now, I'll explain that times 1 a lot more in the future, but for now, just note that I always look at my very last function to be the identity function. And even if I don't write it in my head, I'm always thinking, okay, times 1, because the derivative of the identity function is 1. And of course, there's some cleaning up that can be done here. The 1/2 and the 2 cancel. This negative power goes to the bottom. The x stays upon the top. If you want to turn this back into a square root, you can. You wouldn't have to. You could turn it into a positive 1/2 power on the bottom. But either way, that's what the chain rule says. All right? So, with that being done, let's use the chain rule once or twice more. Give you a couple examples where it comes in extremely handy. Let's say my f of x was equal to a 4x minus x squared to the 100th power. Now, since I have a function on the inside and a function on the outside, without the chain rule, I couldn't take the derivative of this unless I took this binomial, wrote it out 100 times, and multiplied it all out, which is something I would very much not want to do. You have very little chance of getting that right. It would have so many terms. But with the chain rule, we don't have to do that. We just say that the function on the outside is the 100th power function. So the power comes down, drops by 1, and the inside gets copied over. And I'm going to say times derivative of the inside. Well, that's just a polynomial. That is a 4 minus a 2x. Again, power rule. Times derivative of what's inside of that is an identity function, so it's a times 1. All right. Could this be cleaned up a little bit? There's not a lot there that would be worthwhile. So let's move on and try another one. What if y was equal to, we're going to do a little bit of switch up on the notation here, the cosine of a cubed plus x cubed. And this is another instance where I say, always bear in mind who's a variable, who's a constant, and who's a function. All right. So my y prime here would be, first of all, the a cubed plus x cubed is on the inside. The cosine is on the outside. So the derivative of cosine would come first. Derivative of cosine is a negative sign. And you copy over everything on the inside times derivative of the inside. And this, again, is why I said, remember what's what. A is nothing more than a constant. Therefore, a cubed is a constant. So its derivative is 0. Derivative of x cubed is a 3x squared, and the derivative of x is 1. Could this be cleaned up a little bit? Yes, a little. Negative 3x squared will flip to the front. Sine of a cubed plus x cubed is what we have here. All right. Chain rule, by the way, gets used while all other rules are being used. All right, so bear that in mind. Okay, always bear that in mind. It's used in the first derivative. It's used in the second derivative. It's used in every derivative. All right, now, also, something we have to remember. Let's do one more practice problem, just to remind ourselves. Remember that derivative of e to the x is e to the x, and that is true because e to the x is the function that was developed to be its own derivative. But this is not e to the x. There's a sine function. All right, this is a function, being the sine, inside of another function, that being the exponential. So y prime says derivative of e to the power is e to the power. And then the chain rule says times the derivative of the power. Derivative of power, derivative of sine is cosine. Derivative of x is 1. All right? Now this can be used, this is very handy, so that you can take the derivative of other exponentials. Again, remember the derivative of e to the x is e to the x. But if you had y equal to something like a to the x, I want to use an a just so it can represent any other base. You have to use your properties of logs here. Okay, you have to use your properties of logs. Remember, a to the x is e, the power natural log of a, and note that the e and the natural log are inverses of each other, so this is just a fancy way of saying a. E to the natural log of a is the same thing as a to the x. And remember, when you raise a power to a power, you multiply those powers. So this is e to the power natural log of a times x. And again, bearing in mind that since a is a constant, natural log of a is a constant as well. So this is nothing but e to a constant times x power. So therefore y prime would be e natural log of e x times the derivative of the power. Well, a constant times an x, the derivative of that is just the constant. All right? So what's going to happen here, whoops, natural log, turned an a into an e. That's an a. What's going to happen here is, again, the e and the natural log will cancel each other out. So this turns back into a to the x. And the times the natural log of a is there. So that allows you to take something, any base to a power, and differentiate it accordingly. So if I had a y equal a 5 to the x power, then y prime would be, as the rule says, it's 5 to the x, similar to what the exponential e to the x would do, but you have to multiply it by natural log of, I almost said a, natural log of 5 because of that part of the rule. All right, so it's just 5 to the x times natural log of 5 once you take that derivative. All right, so again, the chain rule is always in use. If I was to go on further and use it here, I would say, well, the derivative of x is 1. And again, you're probably thinking, well, the derivative of x is always going to be 1. Why do you write down that 1? Well, time will show. You'll be able to see in time why I do it that way.